Welcome to this last video about the alkylation of cyanide for the preparation of nitriles. This presentation is about the preparation of cyanohydrines by addition of hydrogen cyanide to aldehydes and ketones. This reaction is reversible, and acetone cyanohydrine, for instance, is often used as a source of hydrogen cyanide. Cyanohydrines are important intermediates for the synthesis of alpha-hydroxy or alpha-amino acids. Dehydration of alpha-hydroxynitriles can yield alpha-beta unsaturated nitriles, which are important monomers and intermediates for alpha-beta unsaturated carboxylic acids. Methacrylic acid, for instance, can be prepared from acetone and hydrogen cyanide. This dehydration is, however, more difficult than the dehydration of the 3-hydroxynitriles obtained from epoxides and cyanide. Other industrially relevant cyanohydrines include the 1,3-phenoxybenzaldehyde, which is an intermediate for various insecticides, for instance fenvalerate and cypermethrin. Mandelic acid can be prepared from the cyanohydrine of benzaldehyde, and racemic methionine is produced on a large scale as animal feed supplement from 3-methylthiopropanol as sketched here. Some ketones are particularly unreactive and can only be converted into cyanohydrines with the trimethylsilyl cyanide or cyanodiethylaluminum. In this organic synthesis procedure, the cyanohydrine of benzophenone was prepared with a silyl cyanide and Lewis acid catalysis. The intermediate silyl ether could be hydrolyzed with aqueous hydrochloric acid without elimination of hydrogen cyanide or hydrolysis of the cyano group. Also, beta-ketoesters cannot be converted into cyanohydrines directly with sodium cyanide. Because of the high acidity, deprotonation occurs, and the resulting enolate no longer reacts with nucleophiles. One way to circumvent this problem is by intermediate formation of a bisulfite adduct, as shown here. Alternatively, pure hydrogen cyanide does undergo acid-catalyzed addition to beta-ketoesters. No polymerization of hydrogen cyanide will usually occur if the mixture is kept acidic. Aldehydes or ketones with additional electrophilic functional groups can be difficult to convert into cyanohydrines. In this example, an alpha-beta unsaturated aldehyde containing an allyl chloride was transformed into a silylated cyanohydrine with a slight excess of trimethylsilyl cyanide and a catalytic amount of potassium cyanide, without any solvent. Silylated cyanohydrines of aldehydes can be deprotonated by strong bases and are thus intermediates with inverted polarity. Here, deprotonation immediately caused intramolecular allylation and, after desilylation and elimination of hydrogen cyanide, the formation of a cyclopentenone. In this example, a silylated cyanohydrine of an alpha-bromoketone was prepared with the aid of a Lewis acid in dichloromethane. No substitution of bromide occurred. Even highly reactive alpha-alkoxy alpha-bromoketones do undergo such reactions. In this instance, an aqueous workup led to desilylation. Because of the conformational rigidity of the starting ketone, the cyanohydrine was formed with high diastereoselectivity. Not all alpha-haloketones yield the expected cyanohydrines. Sometimes cyclization occurs, as in this example, to yield a cyanoepoxide. Here, potassium cyanide was used as cyanide source and the reaction mixture was strongly alkaline, unlike the previous examples. Only one of the 3 carbonyl groups reacted. Intramolecular etherification can also yield other ring sizes, and 5-membered cyclic ethers are formed particularly easily. Here, despite being sterically shielded and electronically deactivated, the ketone cleanly reacted with sodium cyanide to yield a substituted tetrahydrofurane in high yield. Cyanohydrines can also be obtained from aldehydes or ketones containing epoxides. Again, Lewis acid catalyzed cyanations with trimethylsilyl cyanide in dichloromethane provide for the mildest conditions and are most likely to succeed. Trimethylsilyl cyanide can also convert ketones into cyanohydrines under basic reaction conditions, as in this example. 10% of tetrabutylammonium cyanide was used as catalyst and no cleavage of the epoxide occurred. In this example, the starting ketone contained 2 electron-deficient CC double bonds and an epoxide. Still, the main product of nucleophilic cyanation under basic conditions was a silylated cyanohydrine. Another reagent suitable for the preparation of protected cyanohydrines is diethyl cyanophosphonate. Even acrolein reacted selectively at the carbonyl group when a diaminocarbene was used as catalyst. Unfortunately, phosphate esters are difficult to hydrolyze, and it may not always be possible to convert these products into unprotected cyanohydrines. Although in most previous examples aldehydes and ketones with additional electrophilic sites could be cleanly converted into cyanohydrines, this is not always so. Cyclohexinone, for instance, often yields byproducts resulting from Michael addition of cyanide to the alkene. Best results were obtained under slightly alkaline conditions in toluene at -40 degrees Celsius. Enantioselective cyanohydrine preparations have been a hot research topic for many years because of the high demand for enantiomerically pure alpha-hydroxy and alpha-amino acids. Most approaches have been enzymatic, but recently strategies suitable for cyanations under anhydrous conditions at high concentration have also been reported. Here, 10% of a chiral Lewis acid and a phosphorus ylide gave a high yield of cyanohydrine silyl ether with 80% enantiomeric excess. If a starting material contains 2 carbonyl groups of similar reactivity, some optimization may be required to attain single cyanohydrine formation. In this example, an aldehyde reacted selectively with potassium cyanide in aqueous acetonitrile in the presence of an alpha-beta unsaturated ketone. As catalyst, an acidic ion exchange resin was used. Also, diketones sometimes react selectively at only 1 keto group. In this example, despite the excess of hydrogen cyanide, only the exocyclic ketone was converted into a cyanohydrine. The reaction conditions were slightly basic, and polymerization of hydrogen cyanide was prevented by dilution with methanol. Even with symmetric diketones, a monocyanation sometimes succeeds. Here, benzoquinone was converted into a monocyanohydrine by treatment with a slight excess only of trimethylsilyl cyanide and traces of potassium cyanide. Let's have a look at some potential side reactions. In the presence of cyanide and bases, aldehydes can undergo benzoene condensation, but this should not happen under acidic reaction conditions. Ketones can be cleaved by strong nucleophiles, in particular when carrying an electron-withdrawing substituent at the alpha position. In this example, an alpha-sulfonyl ketone underwent complete cleavage during an attempted Strecker reaction. Then, if an aldehyde carries a good leaving group at the alpha position, treatment with cyanide can cause oxidation of the aldehyde to a carboxylic acid. Dichloroacetic acid derivatives are readily available from chloral, as shown here. One possible mechanism is sketched here. Only catalytic amounts of cyanide, but an excess of some base are usually required. On this and the next slide there are some more examples which you can also find in the description of this video. That's all I had to tell you about the alkylation of cyanide. Hope you enjoyed it and found the examples useful and instructive. And stay tuned for more videos about practical organic synthesis.